Since 2020, I have been collaborating with a physicist and crystal grower as part of my recently completed doctoral research. He has been active in the field of crystals for optical and piezoelectric and other applications since 1977, and in 2012, together with his partner Corinne Siegrist, he founded BREVALOR as a platform to develop crystals with novel properties for ornamental applications. One of the innovations he's been working on are phosphorescent, or in other words, glow-in-the-dark crystals. The material has similar properties to classical gemstones. Their hardness allows them to be shaped and faceted, and they have the optical appearance of gems. The development of the brilliant cut in history is the documented quest of faceters trying to perfect a geometric cut, applying the laws of optics, that would optimize light emission by reflection in gemstone materials. A light-emitting gemstone material, now capable of storing energy and generating its own light, is taking this quest to a whole new dimension. To speak to me today about his career, the subject of crystal growth, and his thoughts on the future of these and other novel materials for the jewelry industry, I'm excited to welcome Daniel Rytz.
Thank you, Sofie.
Daniel, could you tell me a little bit about yourself and what it is that you do?
I am indeed a veteran in the field of crystal growth. So I've been 47 years privileged to do this in various positions. I spent most of my time in industry, and in about 2011, I had this idea to use phosphorescent crystals, but my employer at that time was not interested in these materials. So I decided with my wife to start a company to keep this technology alive and to find somebody in the jewelry world who would be interested in using these materials.
Maybe going back to the beginning, where do you think your interest in crystal growth came from? And where did you gain the knowledge and experience to become an expert in the subject?
I had at one point in my life as a student to choose among 3 or 4 topics for my master thesis in physics. And I decided to take the topic that was based on nicely polished, glitzy crystals that a potential advisor showed to us students. The advisor was looking to recruit a technical helper, and I got the job, and this was the topic I had preferred, so I was happy with it. At that time, I knew essentially nothing about the art and science to grow crystals, but I learned quickly to enjoy the practical aspects of the work and the fact that from time to time you could harvest a nice crystal, something that is really rewarding to do. At least some of the experiments yielded this joyful experience at the end of the growth cycle. It's not always the case that success is at the end in the form of a nice crystal to see. I worked in several R&D laboratories in the early 1980s, which was a time of some kind of transition. Funding for research and development at that time became more and more a matter of contracts and projects with a very reduced, dwindling academic freedom. So I decided to work in industry instead, where it seemed to me at that time that there was a more direct way to fund crystal growth activity. The consequence of this decision was that I moved geographically from one place to the next, depending on who was buying which company. I have been bought 9 times in my career of 47 years. But on the other side, I had the privilege to be able to stay in the same field for all that time. And of course, over such a long period, you can build up an expertise. To put some numbers on the table, I participated in more than 40 different types of crystals and was probably involved in more than 4,000 crystal growth runs. Mostly, as you have already said, for optical applications, but also for piezoelectric and ferroelectric materials to be used in various applications. Not to omit, I have grown a number of crystals for scientific projects and for relatively exotic ideas at times. And one of these exotic ideas gave birth to the phosphorescent crystals. But most of the time, I have grown crystals for lasers, for what is called frequency conversion, transforming one wavelength of a laser to another, and for piezoelectric materials with very high conversion of deformation to electric field. That is what the piezoelectric does. It transforms the mechanical deformation into electricity.
Not many people know how crystals are grown. Could you perhaps tell us a little bit about one specific material that you have grown for industry? What is involved in this process, and why do we refer to it as growing a crystal?
In the technological work, we have a whole, I would say, panel of methods to grow crystals. But there is an easy way to think about it in simple terms. Crystal growth can be thought of the technique that is used to grow candy sugar from a water bath. You dissolve sugar in water and you induce nucleation points for sugar crystals in the form of what is called seeds. For the case of sugar, usually little strings are used. And then you saturate the sugar bath and you let the crystals grow. The difference in technical crystals is that the temperature is much higher, can be up to 2000 degrees C, but the principle is the same. You fill a container called crucible, you use a nucleation point called seed, and you control the weight and the temperature to keep the crystals growing over a long time. This is called the Czochralski technique, which is the technique to grow silicon, which is the most important technical crystal that you can imagine, because it is the basis for microelectronics, for the internet, and for solar cells. It happens that silicon grows relatively quickly, a few millimeters to 10 millimeters per hour. In the crystals we are referring to today, the growth rate is slower. It's on the order of 1 to 1.5 millimeter per hour, and the overall crystal growth run will take on the order of 1 to 2 weeks. Basically, crystal growth is a slow process, and it takes time for these crystals to reach full size, because what is a crystal? It's an ordered material. It has a long range order over the entire volume. That means the atoms are arranged always along the same pattern everywhere in the entire volume of the crystal. So this relatively perfect order can only be established with relatively slow growth rates.
You mentioned silicon, and you have previously told me that you sort of look at the age that we're living in as the crystal age. Could you expand on why you think we are living in the crystal age?
Yes, with great pleasure. You know that this is one of my preferred references to history, the history of mankind. One can, with some degree of approximation, go back about 12,000 years, and the history of mankind then reaches the era of that is called usually the Stone Age. And from the Stone Age, humanity has evolved to the Copper Age, to the Bronze Age, to the Iron Age. That brings us to about 2000 years ago, when what we call modern civilization started in actually several spots on Earth. And these material related ages, based on stone, copper, bronze, iron, they're somewhat arbitrary, but they last about 2,500 to almost 4,000 years. And this happens to be a unit that I call a Roman Empire. And these material ages last one Roman Empire. Well, I contend then that with the invention of electronics, of so-called transistor elements in the 1950s, in the last century, with that moment, we start the Crystal Age. And the Crystal Age is maybe also going to last the duration of one Roman Empire. So the Crystal Age will be another material related age in the history of mankind.
Is it true to say that we don't quite realize how prevalent crystals are around us?
That is certainly true. Most do not realize that they are daily using crystals. I'll give you the example of silicon. I already mentioned that, but there are others. For example, LEDs, today's prevalent light source that we all are supposed to use to save energy as much as we can. Well, these LEDs are also based on actually a variety of crystals. They are basically most of the time based on gallium nitride single crystals, very thin ones. And these single crystals have to be grown on a substrate, which in most cases is sapphire, aluminum oxide as a substrate. It can also be silicon carbide. There are many more examples, detectors, CCD cameras, and so on. They are all crystal-based, at least the majority of them is. And the amount of crystalline material that we have without knowing it around us in everyday life, this amount is, I would say, ever expanding at present.
You have developed a single crystal material that glows in the dark. You've called it BRG and also BRB. Why did you want to create these materials? And maybe can you also tell us a little bit more about the process with which you grow them or how you engineer this phosphorescing light in the dark effect?
Well, first of all, BRG and BRB, what are the symbols behind that name? Well, they are normal chemical formulas. I will not bother to give them here. That's not important, but they are normal oxides, as they are called. So, what is an oxide? Quartz is an oxide. Rock crystal, SiO2, that's a typical oxide. BRG is very close, and BRB also, to such an oxide. How come these materials were not known since a long time? Well, the material at the basis of phosphorescence, of modern phosphorescence, appeared only in 1994 in powder form. And the idea was try to grow this material in bulk crystal form. This took a long time. Mostly it was a matter of finding the funding. And the crystals were only grown, the first ones, in 2011. And basically, I reproduced the growth machine I have described with the example of candy sugar, except that in this case, the melting point of the material is 1950 degrees C. And the phosphorescence in this material does only appear when two conditions are met. You need a very finely tuned degree of transparency of the matrix crystal. That is the crystal without any additives. Such a crystal would not phosphoresce, but it needs to have this appropriate degree of transparency over a certain wavelength range, that is, over a certain color range, and it needs to accept two or more additives called dopants. What is a dopant? It's a small quantity of atoms incorporated in the crystal, and these atoms will absorb on one hand and emit light on the other. The absorption can be, for example, the absorption of sunlight, and the emission will be the phosphorescence that you see in a glow and in the dark toy, but that you see in a little bit a more sophisticated way in a transparent phosphorescent crystals. I'd like to mention one nice thing about crystals. When you have phosphorescent crystals, unlike with powders, you can start to understand in details what is happening when such a crystal is excited, for example, by the sunlight, and subsequently emits light for a long time. The duration of the emission can be a night or even a day or even several days. It depends on the type of crystal you're using. You can imagine that this phenomenon is quite complicated. With crystals, you can start to understand such a complication quite well, which is another attractive feature of those single crystals.
And you mentioned BRG and BRB. They refer to different colors, right, Daniel?
That is correct. The BRG and BRB actually differ only by one chemical element, but this difference changes the emission of the phosphorescent light. The BRG emits green light, BRB emits blue light, and it's only the difference between calcium and strontium in one or the other of those cases that is responsible for the difference in color of the emission.
And you mentioned previously to me, or sort of explained the process, that there are these so-called traps in the sort of structure of the crystal that capture the light or store the light for a period of time. And you've explained that you're working on formulas so to perfect the duration of that storing and releasing of light. Where are you with that process at the moment, and where are you hoping to get to? How many hours do you hope this crystal will store light for?
I would say that the important parameter to improve the visual appearance of these materials is going to be how high can the intensity be after about 2 4, 6, 8, 10 hours. The effect is such that after excitation, the intensity of the emission, the intensity of the green or the blue emitted light, is at its maximum. And after that, this intensity is decaying. So what we would want to achieve is a higher initial intensity and a higher intensity after a certain period of time. We already were able in the past 8 to 10 years to increase this by about a factor of 2. We do not know at this time what limits us, and there is certainly hope that we will be able to gain more than a factor of 2 in the next few years. There are actually 2 groups in research laboratories working on this, and the progress has been steady and will be steady in the next few years, I hope.
People who think about these lab-grown materials or crystals in particular don't always realize that it actually takes a lot of time to perfect formulas. You've mentioned to me before that timescales to create a crystal are relatively long. Could you expand on that a little bit?
Yes, in general, the time span is long. And the classical revolution in gemstones, in synthetic gemstones, is the invention around the year 1900 by a fellow named Verneuil in Paris. This revolution was that for the first time, mankind could grow ruby, shortly thereafter also blue sapphire, from powders. And this invention is not something that happened within a few months or even within a year. It's the result of more than 20 years of steady work by quite a number of different people. And this is very typical for these crystals. I do not know of crystals that took less than 10 years to be developed from scratch. And BRG and BRB are no exception. The work on BRG has not reached its 20th year, so this leaves room for improvements, but it is more than 14 years of steady work, and that is very typical for crystals.
In my thesis and in our conversations, we have reflected sort of on the history of crystals and as they entered the market, the response of the jewelry industry. And we've noticed that there is some resistance to new materials. How do you hope that the jewelry industry evolves? What do you, as a crystal grower, need to continue being interested in exploring new materials for the use in jewelry?
That is an essential question. Not the question about what will kindle my interest, but the question of acceptance or resistance against these new materials. This resistance is related to different aspects. I will quote 1 or 2 of them. The resistance seems to come for a large part from people who have very strong market positions based on natural gemstones with a high perceived value, a high scarcity, a positive image because nature provided these crystals, and the general conservatism of the industry. How to overcome the resistance against new gemstones? Well, I hope that careful explanations of what can be done with the new materials. The new materials bring a new functionality to gemstones. All of a sudden, gemstones can emit light. Traditional gemstones can only reflect it. This new functionality opens up new avenues to demonstrate hopefully very beautiful effects and maybe also astonishing effects. I like to say that we are looking for the manufacturing of the Fabergé egg with phosphorescent crystals, meaning that with phosphorescent crystals, we hope to be able to do something that for the viewer will be beautiful and interesting.
You have used a few words whilst we are talking: synthetics, natural stones. Terminology has been something that I've looked into in my thesis as well. And the terminology for these lab-grown materials is very much another topic that is very contested in the jewelry field, in this sense. And in my PhD, I've suggested a new word for the materials you create, sort of neo-gemstones. What do you think about the debate that is ongoing about the authenticity of these materials and their description as synthetic, for example?
Well, working with you in these years that led to your very interesting thesis has sort of sharpened my understanding of this issue. On one hand, sometimes you're confronted with difficulties that can seem very difficult to overcome. On the other, you have shown me new ideas in the gemstone world that make me optimistic that the present time is favorable for introduction of new ideas. And yes, we have to get rid of the synthetic stigma. Neo-gemstones sounds a lot better. And we have to explain to the public, maybe also to some manufacturer of jewelry, that the synthetic is actually a word that describes the fact that we grow something. We, the people who grow crystals, we grow a crystal to optimize properties that are as perfect as a growth process allows to make. And this growth process is actually nothing else but a set of natural laws to produce a nice crystal. So synthetic is by no means something that opposes everything against the nature. It's using the nature for, or the natural laws for the production of a crystal, which is a natural structure.
As part of my PhD, you have been mentoring me, and we've been collaborating to investigate the opportunities the incorporation of BRG and BRB materials provide jewelers. What has been positive or exciting about collaborating with a jewelry artist for you as a scientist?
There are two very, very complementary things that come to my mind when I hear this question. One thing that was very attractive was the opening that working with somebody like you in your field and getting a little bit acquainted with your field, it's like an opening to an entirely new world. And it is a world where beauty and craftsmanship play a big role. And especially the craftsmanship aspect, exploring what is possible with craftsmanship, that is very attractive to find new ways to improve crystals. Crystals have all kinds of specific features. Some of them are not favorable for polishing or cutting or gluing, and improving those properties is a very attractive consequence of this opening that you offered me into a new world. Very positive is also to follow, to participate maybe in the steps that come afterwards, after crystal growth, after the crystal has been grown. When the crystal or part of the crystal has to be formed into an object, and this object relates to a concept, and this concept needs to become some kind of tangible reality. Following this process is something that I've learned to enjoy more and more. You have had a concept of a very nice octagon that I personally like a lot, and evolving from the crystal to the octagon, that is a real source for inspiration for more of this type of objects to come.
Yes, talking about these effects, and it's definitely been something that as an artist I've been really compelled by, thinking about these new properties. What do you see as the future for these materials? I know we've been discussing other colors, but what other exciting developments are you working on?
Well, right now, I would characterize what I'm doing relatively intensively is to use patience to advocate and implant the existence of phosphorescent gemstones into what I would call the awareness of actors in the field. That is a task that, well, you know that it takes quite a lot of stamina. The other thing that I have already touched upon a little bit, I am involved, and I'm not doing that on my own. I do that with other people, actually former PhD students in the scientific part behind the crystals. We try to improve the intensity and the duration of the phosphorescence. In a way, we try to improve the efficacy of the effect. Novel colors, you mentioned already, are important, especially the color red for the emission. And something that I want to say here also is to find novel crystal growth techniques. Crystal growth is based on systems that use quite a bit of electrical energy, and it would be very attractive to use chemistry tricks to grow crystals at lower temperature, because you would use less electrical current, and low temperature means better perfection of the crystals. So this is certainly something that is also a topic that we will work on, and we have already started to work on. And finally, I want to offer you a recipe to revisit an idea that is in your thesis. That's the in situ growth of, in your case, rubies on rings. I think one could grow in situ crystals that phosphoresce also on platinum, maybe even on gold rings. And it's a very attractive idea that you have brought in this field in your thesis, and it would be nice if we could grow phosphorescent crystals in a not too distant future. I think the time is quite close for that.
Yes, I'm very excited about that prospect too. Perhaps here we should also say that if anyone is interested in following our developments, they can keep an eye on the website www.neo-gemstones.com because we'll be publishing our collaborative work there as well moving forward. Soon you will set a project, Daniel, for a group of BA jewelry design students at the British Academy of Jewellery. What are you hoping they achieve with the samples that you are providing them?
This question I will answer in a maybe a little bit surprising way. They already changed something without knowing it, these students, by the sheer existence of a relatively large number of people who are going to use these crystals. I had the opportunity, and it was actually the first time that I had this opportunity to learn how to produce small series of these crystals. And this was actually a very important learning step. Together with the BA jewelry students, I look forward to listen to unexpected suggestions, and I hope to learn how to turn these unexpected suggestions into development searches for new avenues, and maybe at the end find the famous Fabergé egg based on phosphorescence. I hope that we will find additional functionalities for the materials we propose, working with shadows, working with projections of light onto some substrate. I hope to find things that I do not even suspect at this time. So I have really very high expectations for this project, as you can see.
When considering the innovation opportunities lab-grown gemstones provide, the glow-in-the-dark crystal materials Daniel has developed are a clear demonstrator of the transformative ability we have to create new crystal materials with properties that exceed the properties of crystals that can be mined from the earth. The opportunity to work with a new material can be inspirational for artists and can enable outcomes that propel us into a new dimension of gemstone creation and incorporation. One where, for example, the sculpting of a material is enhanced with an opportunity to sculpt with light. In the jewelry industry, lab-grown gemstones continue to provoke much debate. This despite some of the benefits they could offer and their creative potential. For, despite all, being interested in pursuing these innovations, for collaborating with me and the students at BHA, and for your time today, I would greatly like to thank you, Daniel. We are very grateful for your efforts.
Thank you, Sofie, for the very nice words, and thank you for this opportunity. It was a great opportunity for me too.
Next month, I'll be joined by another guest, so watch this space to find out who it is. But for now, this was Sofie Boons for the BAJ podcast episode titled Neo-gemstones with Daniel Rytz. Thank you for listening and have a wonderful day.